record. There we go. Cool. Yeah, so hey Dean.
Hello.
So, well, yeah, we're just getting right into the problem because I mean, Paul mentioned that it would be good to see the reactions and review them this chapter, but like, well, this first problem is pretty much all of the reactions, albeit in a complicated form. It is. So
Perfect.
well, we might as
Yeah,
well.
it's all good. Honestly, I have the slides open with me too, so it's review.
Okay. Yeah. Okay. Well, in that case, I don't know. Why don't we? Well, we'll start out from, let's say, this alcohol, right? We'll go top left, and then I don't know. Our plan of attack could be like here, loop back around, and go like this or something like that.
All right.
So, okay, well, let's start out with stuff that's not too bad, right? What about like this direction? If we want to go from alcohol to aldehyde.
I want to throw some NaOCl at it.
That is a good idea.
Sorry if I cut you off, Paul.
No, you're fine. I was going to say the same thing.
Yeah, NaOCl is always a good option. It's not our only option though, so we also have others. So what else can we use?
H2CrO4.
That is a really strong oxidizing agent. That would go all the way to an to an acid. So we might actually want to write that one up here.
Okay.
Can I get a PCC?
Yeah, that's an option.
How about Swern?
Swern is good.
How about DMP?
There we go. Yeah, there's a lot of options to do this, is the point. Yeah, you can make well, you've learned a lot of oxidations at this point, so like, you might as well start using them, right? Okay, cool. And then what about the other way around?
Would those be reducing agents that would convert that back?
Yeah.
So
Can we just use LiAlH4?
Yep. Okay, and that one's kind of overkill, so we could use a much milder reagent instead.
H2PD.
Oh, can you? Yeah, you could probably do a catalytic hydrogenation on this one. I was thinking of a different reducing agent, but I bet you could.
So would ZnHG reduce this to a point where it would just become an alkane? Or,
Yes.
oh, okay, got it.
Yes, I think it would.
You use NaBH4
Yeah.
for hydride.
Yep. Yeah, no need to go really crazy on that. Yeah. Okay. So that's good. Yeah, okay, so this is like a lot of reactions that we've learned kind of packed up into one thing. This is something that we've like done a lot. Same thing with alcohols and acids. So we have chromic acid is one, but there's also, what else can we use?
Excess NaOCl tempo.
Yeah. Tempo. That's a good one. Other options? These are like the good ones, right? But
Let's see.
Yeah, I think this is probably it. I bet you could do some stuff with potassium permanganate, but that's like, I don't think we've at any point officially learned that, and that probably gets too messy anyway, so we could just leave it at these two.
I think I saw it in the PowerPoint somewhere, but no, it's just another option, right?
Yeah. Also, at this point, hopefully you guys are familiar enough with potassium permanganate that like, if you see it somewhere, you realize like, oh, I'm oxidizing the hell out of this, and so you might as well just oxidize whatever you can, because that's about as strong as of an oxidizing agent as you can get. Cool. What about alcohol back to acid? This one's a bit more involved, although you've done it before anyway.
You mean
Wait, alcohol to
aldehyde
acid?
acid?
Sorry, acid to aldehyde, or sorry, acid to alcohol.
Oh, okay.
This top arrow up here.
Could you use the same reducing agents that you used for the aldehyde?
Yeah, I would use the
All of them.
LiAlH4.
Okay, yeah. H4. Okay. Good. Is that your only option?
I'm sure it's not.
It's not.
That's the one I could think of.
Yeah.
Um,
And the point is, all of these reactions that we've written down so far are a review, but now there's an actual new one.
oh, okay. Then I don't know it.
Okay. So we're looking for acid to alcohol, right?
Mhm.
Okay. Oh, BH3 THF.
Yeah.
I think we heard that one in Orgo 1.
I think, but I don't think we used it for this though, did we? I remember that like reagent or that reagent, but I don't remember that like. I think we did something weird with it before.
Yeah. Earlier we used it a lot for hydroboration.
Yeah, that's right. Hydroboration oxidation.
Yeah. But for this, it's a bit different.
Okay, cool.
Yeah.
Is it BH? We need H3. Okay, yeah, H3.
Yeah, and then you do aqueous workup at the end. Yeah. Okay, and that'll also work. So what is the benefit of doing this one in the first place? Why wouldn't we just use lithium aluminum hydride? Like that worked perfectly fine before.
Would that not touch double bonds?
Oh, and it also wouldn't touch aldehydes and ketones, right?
Yeah, so this so this only works on acids. As opposed to ketones and aldehydes, I mean. If you have a double bond or triple bond in your molecule, then you'll get screwed anyway. But
okay, so it'll also reduce the alkenes. Okay.
mm-hmm. Yeah, although you kind of get stuck because like you'd wind up getting like, let's say you have this like molecule that has like a double bond and an acid, right? And then you wind up doing this, right? You'll wind up with, well, at least on this end, you'll certainly wind up with this BH3 or BH something, maybe like a BH2, I don't remember, and then some other stuff over here, right? And so you'll wind up with this, and then normally we need to use hydrogen peroxide and base to get rid of it, or we have to use actually I think that's the only option that we had anyway, but we're just using water at the end of the day, so it's unclear if that'll actually remove this borane or not. So if there's a double bond in there, things might just get kind of freaky in your final product. You might just wind up with something left over.
Okay.
So yeah, I guess just in general, this isn't a good reaction to do when there's double bonds, but yeah.
So just avoid double bonds when using BH3 and THF.
Yes. Unless you're doing it for hydroboration.
Oh, okay, true.
Yeah. But, oh yeah, then if you're doing hydroboration and you have a carboxylic acid on your molecule, then you have to deal with that too. It's, yeah. I haven't seen any case where there are two of those functional groups on a molecule and you're like expected to know that it does both things at once. So I wouldn't maybe worry about that one too much. Yeah. Okay, cool. How about this arrow going from an aldehyde to an acid?
Couldn't we use any of our really strong reducing agents?
So
Oxidizing.
we want to use oxidizing, right?
Yeah. So NaOCl excess or H2CrO4.
Yeah. Excess NaOCl will do the job.
Okay.
Or yeah, chromic acid. Either one is good. Right. And of course, I mean, these are all completely general reactions, right? So like we just have these specific compounds, but if we had any alcohol that we wanted to make into, well, any primary alcohol that we wanted to make into an aldehyde or an acid, or we can go to an acid chloride and so on, right?
For acid chloride, is it just SOCl2?
Yes. So we have SOCl2. That's good. Yeah, there's also another option though. It's not just SOCl2.
Or PCl3.
Oh, is it COCl2?
So it's
CO2Cl2? I mean,
yeah, CO2Cl2.
oxalyl chloride.
Yeah, exactly. It's oxalochloride is the
Oxal. Okay.
one. Which looks like this. That's another option. Okay. And now is the part where I ask you to dig through your mind. Where have you seen oxalochloride before? You've used it. It's not new. In fact, it's even on this page somewhere.
Oh, it must be, is it Swern or DMP?
It's Swern. Yeah.
Okay.
DMP only uses one reagent. And it's this really big specific thing that's like something like this. And there's like another ring and there's like an iodine and like a bunch of junk hanging off the iodine or something.
Okay.
Yeah, Swern uses also a lot of stuff. Well, Swern actually does use a lot of stuff, but the thing is, it uses this oxalochloride as like one of the really key reagents.
Okay.
And so you have worked with oxalochloride, although it's usually just been written as Swern. Yeah. Yeah, it depends on what Dr. Tong wants from you guys, but I know when I took 242, this was a mechanism that like we were really supposed to know. Or at least my professor always said like, oh, if I were you guys, I would learn the mechanism, because in the book it shows the mechanism for SOCl2, but it doesn't show the mechanism for oxalochloride. And my professor was always like, if I were you guys, I would learn the mechanism for oxalochloride because it might show up on an exam. And then it like obviously showed up on the exam. So
Our PowerPoint just shows the SOCl2 mechanism.
yeah, Yeah,
I
if
mean,
Dr. Tong didn't even mention oxalochloride, then
it's there. It's there on like below the arrow. We have an arrow with SOCl2 on top, and it says or oxalochloride. But the mechanism that he drew out is for SOCl2.
Would it be the same thing? Like, would the carboxylic acid oxygen attack the carbonyl carbon of COCl2?
yeah, it's something very similar. I think at the end of the day with this thing, you wind up evolving CO2 and carbon monoxide, I think. And so that's like the only difference. Whereas with SOCl2, I think you wind up evolving SO2 gas, but yeah, I might be mistaken. But otherwise, it's the same mechanism. Or very similar. So it's just worth keeping in mind that like that's something that is valid that you might be asked about. But if Dr. Tong, I don't know how much he normally signals what questions he's going to ask about, but
I mean, usually if he doesn't draw out the mechanism for a molecule, it's
Okay.
not something we worry about, I think.
all right. Well, in that case, maybe I wouldn't worry so much about it. Cool. Well, then let's just keep going then. Cool. Let's go acid chloride to ketone this way.
Could we just do that with an Na CH3? Oh, wait, no, you couldn't do that.
Yeah, you can't make that.
Yeah, never mind.
Okay.
We
Oh.
can't do LiALH, whatever, the OT butyl, that weird reagent. Oh, can you do diabol?
Oh, so you could use one of those to go from acid chloride to aldehyde, which we actually forgot about. So you would use here, you would use this lithium aluminum hydride butoxy thing. So you would
Okay.
use that in that direction. Because this one, for whatever reason, likes acid chlorides and reduces those specifically. And it's a good option, I guess.
Could we do like a CuCl or what is it when it has like two of them on it in parentheses, and then it's just like whatever the chain is, and then or could we do, Grignard, right?
So let's write this one, the cuprate. That's a good option. Okay, let's say we were to use a Grignard, right? Why don't I write it like down here? Right here was the reaction. So it was, if we give it methyl magnesium bromide, this guy is going to attack on there once. We're going to get this ketone. But the thing is that this guy is also really strong. Grignards are very powerful, so it'll attack on there again because these things can attack on ketones twice.
Mm-hmm.
And so we'll wind up with a tertiary alcohol at the end of the day.
Okay.
Yeah. The nice thing about cuprates is that they kind of suck, or at least they're bad at the reactions that they do. Like they're weak is the point, right? So they'll react with acid chlorides because these things are super reactive. These are like excellent electrophiles. So we can react once with it. And then dimethyl, right? But once we're here, ketones aren't reactive enough, so it'll stop.
Mm-hmm.
Yeah.
Is that
So this is
UBR dimethyl then?
Yeah.
Okay.
Yeah. So this is exactly the way to do it. Yeah. Let's use a cuprate. And I think it might be the only fast way to do it. I don't know if there are other good ways of doing it quickly. Cool. Acid to ketone.
Oh,
Do we want to go here?
we do have that in the PowerPoint somewhere.
Let's see here.
It-
Oh yeah,
two
R.
RLI. Yeah,
Oh, sorry. Yeah, go ahead.
Okay. Oh, so 2 times
the
RLI.
organolithium. Yeah.
What is R?
In this case, it's just going to be a methyl.
Yeah.
And
Yes.
Dr. Tong told us that after researching in several books that this can't use organolithiums, it could just use, or you can only use organolithiums, not Grignard,
Oh,
I think.
okay. That's kind of
Yeah.
interesting. Huh. Okay. That's pretty cool.
Forget what his reasoning was for it, but I believe just said they
Yeah.
can't be used.
It might just be, I'm pretty sure lithiums are stronger than Grignards at the end of the day. So it might just be that like this is actually just a better thing. Although maybe it's also some like really high level stuff that is way out of our reach. So it could very well be that too. Yeah. Cool. Let's see, where else are we going? Why don't we just take care of this nitrile
Okay.
quick? And we're going nitrile to ketone.
Nitrile to ketone. That's crazy. Would that be in our amine?
You could do just Grignard or organolithium, I think.
Okay. So one, let's give it a Grignard just because, you know, we used the lithium for the last one, so why not? Okay. Well, if we write out that the mechanism there or the reaction, this guy
Could we
coming
make a
in.
carboxylic acid first and then make the ketone from the carboxylic acid, or is that like a roundabout way?
Let's see, you're saying make a ketone from a carboxylic acid.
Yeah, because we have a reaction in our slide deck to make a carboxylic acid from a nitrile, and we know how to make a carboxylic acid into a ketone.
It's an option. It's a bit involved.
Yeah, if there's a better option, please.
Yeah. So, I mean, using this Grignard is not a bad idea, right? So if we use this
Okay.
Grignard, we'll get up to here, right? And so it's kind of ugly. So it looks like this, which looks like what functional group with the nitrogen?
Imine?
Yeah, so it looks like an imine, except it's not, it's deprotonated.
So
Kind of looks like a ketone.
Yeah, exactly. So we can aqueous work up this, get an NH, right? Okay, but we're already in acidic conditions, which goes to a ketone.
So just Grignard and then an acid workup.
Yep,
Cool.
that is it. Yeah. Cool. All right, let's look at the secondary alcohol. It's over here now.
And we want to make, or do we want to make the ketone, or are we?
Yeah,
going-
sure. Let's go this way.
Okay.
Let's go secondary alcohol to ketone.
Isn't it pretty much everything that we use to get a primary alcohol to an aldehyde makes a secondary
Yes.
alcohol a ketone?
Yeah. All of these are fine. Maybe I'll write them out just because oxidations can vary based on what you're doing. Okay. Those are all good, right? And then reduction. I don't think it's a surprise if I tell you the reductions are all the same as well, right?
Mm-hmm.
So lithium aluminum hydride is good. Catalytic hydrogenation. And a BH4 is good enough to do this reaction. Yeah. Okay, those weren't that interesting. What about aldehyde to a secondary alcohol?
Could you H2SO4? No.
No, it wouldn't work. Well, we're adding an extra carbon, right? Because here we just have something with 2 carbons, and here we have 3.
Okay.
Yeah.
Could we use a Grignard?
Okay.
I thought of something, but it's terrible. It's you add a nitrile and then you take off the nitrogen, which is, I mean, I'm just remembering the most recent reactions. It's
Ooh,
Yeah.
that is involved.
not what you want to do. I understand that right away.
That would be kind of interesting, though. I mean, you could do like this,
Reduce it to the NH2, then you deaminate.
stick on this nitrile, right? We get like this and this thing, right? And then from there, I think you just do acidic workup. Then you get here. Oh, this is just a hydrogen. So really, it just looks like this, right? And then I think at the end of the day, you wind up with, is it a carboxylic acid? When you hydrolyze a nitrile?
I know that there's a reaction that we learned for the amines where you convert the nitrile to an amine and then you can deaminate just so you're left with carbon, that single carbon you added.
Okay.
I'm sure it's a terrible way of going about
It
it.
depends on what you use here. It is kind of involved, you're right. Although
Paul,
I
are you
imagine
thinking
there's some way you could do it. There's a lot of reactions with these things. So.
Paul, are you thinking of the quiz question that like would have helped to add that carbon using the nitrile?
Yeah, and then I would have done it that way. Then I would have made it an amine. Then I would have H2PO4'd it
Mm-hmm.
and just be left with that carbon. Yeah, I mean, I use the most recent reactions because that's what I remember.
Yeah, which is fine. I mean, given that the questions that you're going to be asked are always to do with the most recent reactions. Yeah, it makes sense. Not a bad strategy. But in this case, now this one we could just use a Grignard, right? Aldehydes will only react once because you can't take off that hydrogen. So in this case, that's all there is. Nice. Okay. Now we're almost at the end. Let me get rid of this stuff at the bottom because now it's just in the way. Okay. Excellent. All right, cool. And let me get rid of this extra junk too. Let's say that we're going, let's do this side over here first. Let's go acid to ester.
So could we do the Fisher?
Yeah. Yeah.
Just use an
That
alcohol.
is, that is definitely the way to do it, right? So what alcohol should we add?
Just
Ethanol?
methanol.
Yes. Okay, methanol and what?
Let's see, acid, H3O plus.
Sure. There's one option. I'll replace this instead with sulfuric acid because in practice, I think that's the most common
Okay.
choice for Fischer esterification. But
So it's not sequential, it's concerted. It's not methanol, then H2SO4. It's
yeah,
the same
the
time.
acid is actually a catalyst.
Oh, okay. Okay.
Oh, awesome.
So, yeah, it is just one reaction. You just throw it all in together in one pot. Yeah. Yeah, I don't know if any of you are taking Orgo Lab now at this time. Also.
Yeah.
Yeah. Yeah, we did a Fischer esterification. I'm also taking Orgo Lab now, which is a little bit freaky, but maybe
Excellent.
don't worry about it. Yeah, we did a Fischer esterification recently where we did like I think benzoic acid and some alcohol. I can't remember.
Oh yeah, and Beyond Labs. Yeah, no,
Yeah.
I remember that.
Yeah.
I'm surprised you remember even one of the compounds that was involved.
Yeah, it was the one of the recent videos. It was one
Yeah.
of the ones that they even did in person, because they just went and like, they had this like big reflux, and they just added I think like benzoic acid was one of the things. Yeah, because yes, and then they added also. It was probably just methanol, right? Because remember, then we made this ester.
Bless
Thank you. It's my roommate.
you.
Yeah, we made this ester, right? And then we used Grignards a few times.
Mhm.
Anyway, this is not Orgo Lab, so we don't have to worry about this. Very fun class.
And there's the way to.
Okay. Well, we just have these three reactions left anyway, right? So what is there? Well, let's go from ketone to this alcohol first because, well, I think it'll be useful for the next reaction. So let's go from this ketone to the alcohol. That's a good option.
One quick question, since we're not doing the reverse reaction of this ester back to the carboxylic acid, could you use, it's just acid and heat, right?
Yeah, so if you want to go from ester back up to an acid, so yes, you need heat, and H2SO4. So yeah, H2SO4. The thing is, in this case, if we're going from acid to ester, then we want to use excess methanol because that'll really like force the methanol onto the molecule because there's just so much of it. If we're going the other way, we want to use dilute H2SO4, meaning that we have a ton of water around. I mean, we could write either dilute H2SO4 or we could just write water in explicitly, but the point is that it's dilute. That's the important part.
Got it.
Yeah. But you're right. This is an equilibrium reaction. So really there's like a tiny arrow going this way.
Got it. Thank you.
Yes.
For the ketone to the alcohol, could we do the same thing with using a Grignard and then acid workup?
Yep. Yeah, these
Oh, cool.
this is the same move as before. Okay. Now what about ester? To an alcohol, to the tertiary alcohol.
Ooh. So we can go ester to carboxylic acid by doing that H3O plus and then heat. And then we can do carboxylic acid to alcohol somehow. Didn't we do that earlier? No, maybe.
Yeah.
There is no
did.
way to make a carboxylic acid an alcohol, is there?
Yeah, so we did this earlier where we went from acid to ketone. It was this reaction. But then we're missing a carbon. Right. The best here we could do is just to get this ketone. But that's the best we could do.
Okay.
So this step isn't it, because then we're just stuck with the acid. Yeah.
Well, if we
So actually, what I was drawing up from Orgo Lab earlier is actually the relevant part here, because in Orgo Lab, what we did was we went from here, we went to this ester, and then we did some stuff, and then at the end of the day, we got this big alcohol. I mean, not that this necessarily helps, because Orgo Lab is confusing as all hell, but if you do remember what the recent reaction was here.
Grignard.
Yes, it was.
So if we do Grignard and then acid workup.
Yes, exactly. Yeah, the missing reagent here was the Grignard. It was just phenyl magnesium bromide, this thing. Which in Orgo Lab involved, like, you know, you had to like actually make this thing. So you had to get like this thing and bromine and then add the magnesium and do all of that. But, you know, at the end of the day, the actual reaction that was happening was this one.
So a Grignard to an ester can reduce it to an alcohol. Okay.
Yes.
Interesting.
Yes. So here we need methyl magnesium bromide. And you'll also notice that we need 2 equivalents, because we have to kick off this ester.
Yeah.
Right. We have to kick off the ester to make a ketone, and then we add again to make the alcohol.
Can we just say excess because it's a tertiary alcohol?
Yeah, you'd be fine if you just said excess. Although like the exact stoichiometry, is the word.
Yep.
Is 2 to 1. Yeah. Right. And then, I mean, you already know it's an aqueous workup after too.
It's almost confusing with how much a Grignard reagent can do.
Yeah, they're pretty powerful. Yeah, they are pretty strong. I guess just in general, when you see like something that has like a ketone or a carbonyl on it, you could probably attack with the Grignard. I guess the only exception is when there's an acid, right? In which case you have to use a lithium, but otherwise they're totally interchangeable.
For the acid chloride to the tertiary alcohol, would we be better off making the acid chloride into an ester and then converting it?
Okay. I mean, that would work,
I
certainly.
would just use an alcohol, and then I would get my ester.
So like
Uh,
methanol.
Yeah, methanol here, and then same thing, Grignard.
Okay, that works. What is the benefit of adding the methanol?
The methanol makes it into an ester, doesn't it?
Okay, yeah, I know. So we're going this way, right? And then we're going this way.
Mhm.
You probably don't have to do that. I mean, this chloride itself is a great leaving group.
Oh, okay.
So, in fact, we could just,
Grignard it.
yep, we could just
Two
take it right
equivalents?
off.
Whew.
I'm feeling a general theme here. When in doubt, default to your Grignard.
There are, yeah, a lot of these reactions you could do with Grignard. This problem is pretty Grignard heavy.
Okay.
So it's not like in general you just start blasting things with Grignards, like you know.
Okay.
Honestly,
But-
though, I like them better though than diazonium salts. I didn't like how many things you could do with those.
I think diazonium salts are like one of the coolest things in Orgo. Just because, like, you know, I don't know. I guess you spent all that time in one of those like some chapter about aromatics, learning about, like, you know, how to do EAS and like nucleophilic aromatic substitution and all of those like really complicated reactions. And then at the end of the day, someone comes on with a diazonium salt and just starts swapping things out, like, you know. Yeah. No, those are pretty cool.
I'll give it to you.
Yeah. Same thing with, like, I'm pretty sure Dr. Tong actually did cover those coupling reactions. I think one of them was even on your quiz, which is
Yeah.
pretty surprising.
I don't think it was
Even
on
though
our
they're,
quiz.
like,
I don't
it
remember.
wasn't? No.
I don't remember.
Okay.
We just had a complex amine to nitrogen like charged, or like a tertiary, or no, quaternary amine that we needed to do.
Oh,
in
that's
terms of,
pretty
like,
weird.
Oh, I didn't use I didn't use the coupling for that.
Yeah.
Oh no,
neither did
I didn't mean on this recent quiz. I meant like a few weeks back.
Oh,
Yeah, whenever you learned about the coupling reactions, I don't remember when that was. The Heck and Suzuki couplings, and I think you could do some of them with organocuprates too.
Mhm.
Those are
but
also
yeah, we
some
had
of the
those. I was
coolest
thinking of the
reactions.
coupling with the nitrogen based.
Okay. Yeah. Oh yeah, there's something about like azo coupling.
Yeah,
Yeah.
azo coupling. Yeah.
Yes. Okay. Yeah, I remember that. Yeah, I don't know. Those coupling reactions are also some of the coolest, in my opinion, because they also just let you start sticking things onto other things, like, you know, without regard for all of the other reactions that you've learned in organic chemistry. They are pretty cool, in my opinion. Yeah, they also, I mean, it's kind of just because, like, they like kind of break organic chemistry, at least as far as like we learn it in these classes. Yeah, those reactions are like super broken because they just let you do really complicated stuff really fast. So they're pretty cool. Cool. All right, well, that covers this big map, which, I mean, honestly includes probably most of the reactions from this chapter, I think. Maybe there are more that we missed.
Yeah, we didn't. Let's see here. Did we? Yeah, we didn't really play with nitriles. We did some stuff with, I think, nitriles. No.
Yeah, Yeah, there's some more about nitriles. I also am reminded there's an extra reaction that this is missing. Well, we did it, we just kind of didn't include it. But there's just an alternate way. So if we have an acid and we want to go to, let's say this is our acid and we want to go to a, I'll be a bit more specific now and say a methyl ester.
Wait, we did that, the Fisher esterification, right?
We did, but there's another way to do it. And this way is actually a lot stronger. The Fisher esterification was an equilibrium. This one is not an equilibrium.
Is it the diazomethane?
Exactly. Yes. Diazomethane is another one. So this is just CH2N2. Yeah. And well, why is this a good reaction?
Oh, because it's going to be specific. It's going to get you high yield.
Yes. Yes. This reaction has like excellent yield. Like very few things in organic chemistry have this good yield. The yield is good enough to overlook the fact that this is like extremely explosive and like a terrible thing to work with. Yeah. My professor, when I took 242, always was talking about how like when he worked in a lab, somebody would walk up to him with a bottle of this and be like, "Hey, you ready to do the reaction?" And he just left the building because it was going to blow up. So I don't think it did, but this is not a fun compound apparently. I'm pretty sure. So I was actually looking through my notes about this chapter before, and I remember I wrote down apparently last year that you've seen this compound before and it's been used in a different reaction. I can't remember what that reaction is. So if anybody can think of what reaction you've seen before that uses diazomethane, let me know. But I don't remember it.
I can't remember, but I feel like we would have remembered because Dr. Tong was also very like cautious about this reaction. Like he's like, this is very dangerous.
Yeah. I don't remember where. I don't think it had to do with one of the diazonium things. I don't think so. I was looking up diazomethane earlier and couldn't find anything. So, so I can't remember. Maybe I'll look through some of my old like notes or something from when I took 242 and find out. But
you can use acid chlorides. Yeah, it works with a lot of things. It works with esters, or it works with ethers. Not ethers, ketones, acids, alcohols. Oh, it might have been in the alkyne reactions, perhaps.
maybe. I don't know. I can't remember. Yeah, and then I was stuck for like a while this morning trying to remember like why would I have written that? I don't remember what reaction we used it in. So let me know if you think of it or find it. I guess I am pretty sure that diazomethane is used in a lot of stuff. I just don't remember like what reaction that we've seen. It might have also been specific to the section of organic chemistry that I was taking when I took the class. It might not be a thing that like every professor covers. So
it also does make cyclopropyl groups with alkenes, which might be it.
That part I saw. I don't know if that was it, but maybe it was. That was probably, maybe that was it. Maybe that was what I was thinking of because I saw that earlier and I thought like, I don't know if this is really specific enough that we would remember.
I don't know, we might have used it to form epoxide rings out of ketones as well.
I've never heard of that, but that's pretty cool. That is a cool reaction. but yeah, it was probably using it to make the little triangles. Yeah.
Mhm.
Cyclopropane rings. You guys know naming, so I should actually say that instead of calling them triangles like usual. Okay, there's one extra part to this problem, although it's separate, and it's also very small, so this part is fast. Okay, monitor. Here we go. Yep, this is it. It's just these two reactions. They're not even new reactions. We have a terminal alkyne, and in one of these cases, we're doing hydroxymercuration, or it's just oxymercuration, right? And then in the other one, we're doing hydroboration. Yeah.
Let's see here.
The oxymercuration makes a ketone.
Okay.
And then the sodium one makes an aldehyde.
Mhm.
Yeah, that's it. Okay. Yeah, that is the whole problem. Maybe also really importantly, because I mean, well, you guys have learned these before, so I don't expect that you'll be asked the mechanism of them again, but it's good to know. And I mean, we're not going to go through the whole mechanism, but there's one key step that's involved in making both of these, or one key part of the mechanism.
There's an anole that's formed.
Yes. So at some point, you have to do a keto-enol tautomerization. Is key for this reaction. Okay. And I know that this semester I point out keto-enol tautomerization every chance that I get, as do most professors, and it's really not clear why, but it will be in 2 weeks when you get to the last major section of all of the organic chemistry you will ever learn, which has entirely to do with ketones and enols. So I promise keto-enol tautomerization will be very important. In fact, it is very important, and you'll find out why soon, but it's worth pointing it out anyway. Okay. This next problem is quite large, so why don't I make this is the only other problem, but it is very large, so why don't I save this? I'm gonna make a new document, and except it's gonna be a different size because I'll just make the whole page as this document. So this is, I don't know, it's probably like, okay, whatever. Make another big page, and all right, let's copy this. There we go. Okay. Except it's very small.
You weren't kidding about the size.
Yes. There we go. Okay. It's big. Where'd it go? There it is. Okay. And I need to make this brush larger. Okay, because this page is very large. Okay. So the whole thing is to solve all of these, which is quite involved. So why don't we take a step at a time? These are kind of labeled by letters as well. So there's kind of like groups of questions here. So why don't we work on A first.
Mhm.
We'll do A, and then we'll move on to B and keep going.
Cool.
Okay. These are all of the reactions in A. So why don't we just not worry about anything else besides these 6 reactions?
So let's drop the alcohol out of chlorine.
Yeah. Okay. Cool. So right away we're getting rid of. Whoops. We're getting rid of that whole thing, right? Replacing it with the chlorine. Good.
And then now drop the chlorine, add an NH2
For this one.
for
Yeah.
A5. Oh yeah. Oh, sorry. If we wanted to go to the end, A2. Sorry.
No, it's okay. I mean, the order of this, actually, this is a more sensible order anyway. Okay.
And then this one's weird. Cl2.
Let me check if this is a reaction that we know.
Doesn't look like we did anything like this with our. I mean, would it be aromatic substitution of aryl amines? No.
No, I don't think we've done this reaction.
I guess could we just get to it from A3?
Yeah, we might be able to. Let's go this way instead. What is this azide doing?
Just going to replace our leading group.
Yeah. Okay.
Okay, so then we have that. 3, and then heat.
I don't think we've seen this reaction either. Yeah.
I think the only thing we've learned out of azide is the LiAlH4 and H2O.
Yeah. Yeah, let's fill in, let's just fill these in. This is not one that you've seen before.
Oh, whoa.
Yeah. You will see another compound like this at the very end of the course. When you talk about protein chemistry, you will see this is called an isocyanate, I think. You'll see another one way down the line, but I don't think it's even normally covered how to make them, so maybe don't worry about this one so much.
So
Just going to be a primary amine because we're just losing the CO2.
Yes. Yeah, it is. It is. Yeah. I wouldn't worry about either this reaction or this reaction. It's possible that this is something that maybe we've seen before and none of us are thinking of it, but I don't think so. Yeah. Okay. And this reaction with the alcohol, we haven't worked with isocyanates yet either. So yeah, this is not that exciting of a question. And I could just, it's perfectly fine if I just tell you, you make an ester out of it. Yeah, these are not things okay, all right, maybe starting off with A was not that great. All right, whatever, we got them out of the way. Why don't we do B instead, which goes, B is all over the place. B is blue. This here.
is-
2,
Is toluene the like cyclohexane with a nitrogen?
With a methyl.
yes,
Oh yeah.
it's benzene with a methyl. You were thinking of aniline, which has an amine on it.
There it is.
Yes.
Okay, so both edit there. What is LAH?
Lithium aluminum hydride. So
Oh.
LiAlH4.
Oh, okay.
Yeah.
And that is a so that will make an alcohol on that ketone, right?
That sounds pretty reasonable. All right, let's zoom in on these, and I guess we'll take them one at a time anyway. Why don't I just use blue to do these? Okay. You said make an alcohol, right?
Mm-hmm.
Yeah. That sounds pretty fine.
Are the majority of these reactions chapter 20 reactions? Sorry, I feel like I'm seeing some things that I don't recognize from recent stuff.
So I think a large portion of them are.
Okay.
Yeah, a few of them are. Some of these are definitely review. Some of them, I mean, like these 3 are just those ones we don't have to worry about that much.
Okay.
Yeah. There a lot of these are review questions though. Right.
Okay, so alcohol in acidic conditions with heat.
Won't that just take off the alcohol?
And
Makes a good leaving group. Like protonate the alcohol to water and then a good leaving group. Is that right?
yeah. So it leaves, and then
Right.
what does that make?
An alkene?
Yeah, there we go. Exactly. So we have an alkene now. Okay, let's go to B3. This is an old reaction, right?
Oh, that's
I think you also need hydrogen peroxide here, but
are we splitting the double bond?
and
Analysis.
okay. Oh, so you mean into 2 separate compounds?
Yeah.
No.
No.
That would be if we did something like ozonolysis.
Is that would this put alcohols on both sides
Yes.
of the double bond?
Yes, it would. Yeah, this is a syn dihydroxylation. Like that. And of course, notice that there are wedges because stereochemistry.
Oh, because it's sin. Okay.
Yep.
And then would B4, would that do a chlorine to the more substituted side?
Do the rest of you agree?
I'm just copying. I would say, yeah. I would say more substituted side.
Yeah. Yes, it would.
Okay, and then are we making
Okay.
we're not making a
Actually,
what?
so maybe let's linger on this one a little bit. Let's, for a brief moment, take a look at the mechanism.
It's the blam, right? Similar
What is
to the
blam?
epoxide, blam, acid was substituted.
I remember seeing this acronym, but I don't remember what it stands for.
If it's a base, you go to the less substituted. If it's an acid, you go to the more substituted.
Oh, okay. Yeah, that's a fun acronym. I guess just the reason that maybe we should think about this one carefully, is that there's something that kind of changes the idea of more or less
Oh.
substituted.
It's the what is it called? The benzoic carbon, or no, the
Benzyl.
benzyl.
Yeah, there's a benzylic carbon here,
Oh,
which is
okay.
always better. Yeah. If you feel bad that you missed it, don't worry, I did too. And then I just barely remembered. So yeah, it's worth mentioning. You guys are almost at the point of organic chemistry where like you've learned as much of it as I have at any point. So like, we're all working through these problems together. Yeah. All right. We add magnesium. What's that make?
Grignard?
Yeah, it makes a Grignard. We add CO2. What's that make?
I don't know that one.
Okay.
We ever
So
use
we
carbon
have-
dioxide as a reactant?
Yes. It's kind of interesting. I didn't know about this until I had this question on an exam and I did not answer it.
Oh, we're making a carboxylic acid.
Carboxylic acid.
Yes.
What?
Yeah, it's pretty cool actually. When you think about it, carbon dioxide is just a big ketone, except it's kind of a ketone in both directions. So you could just do the usual reaction on it. This will make an acid.
That's crazy.
I know. It's pretty cool. Right? Yeah. It's also good to find out about it when it's not on your exam.
Yeah,
So,
that would be helpful.
yeah, I know. Yeah, this is one such reaction. The other reaction from this chapter or this unit that kind of screwed me on one of these exams, which I think I got on an exam before it was actually taught, was that you could use BH3 to reduce acids to alcohols. That one's also weird, and my professor didn't teach us that one and asked it on an exam anyway.
That sounds fun.
Yeah. So I always associate mentally this reaction with the one about BH3, just because both of them were asked in my exams without actually being taught. Anyway. Yes.
And then
at the
will
end of the day-
that oxygen ion or the deprotonated carboxylic acid just become a carboxylic acid? Okay, perfect.
Yes. Yeah, because we do an acid workup.
Perfect.
So,
And we're not going to forget the next reaction because you said how dangerous it is making an ester, right?
that's true. Yeah. As it turns out, associating stories with reactions is very effective for remembering them, because I still remember this reaction quite well from my professor's stories of how he didn't want to blow up in the lab. So it works pretty well.
Okay, so this is a B7 is a Grignard reagent. So
There's a lot more B's.
then would we just do a little nucleophilic attack of our carbonyl carbon here?
Are you guys just writing on the PDF on an iPad or something?
Oh, I printed mine out.
Oh, that's also smarter. Okay. I was gonna say mine looks terrible in my notebook.
Yeah, I know. When this was in person, I'm pretty sure we had this same problem last year. No, maybe by this point it wasn't in person anymore. So maybe I did this online as well. But writing something up like this on the board would have been absolutely terrible. So I'm very, very glad. Well, there are some benefits to doing this online. This is one of them. Yeah. Okay. So you were saying we had.
So since we have two equivalents, we're gonna kick that ester oxygen out of there, and we're gonna add two methyls.
Yes.
And it'll become a tertiary alcohol.
Indeed, it will. Yes. This is the Orgo lab reaction. The one thing that we will learn from Orgo lab this year might be this reaction. Otherwise, who knows? Maybe not anything.
And how to read an SDS document.
Yeah. I've become a god at using PubChem and Reaxys to answer all my pre-labs. Yeah.
And ChemDraw.
Very useful class. ChemDraw. Yeah. The baller move would be to do these entire workshops in ChemDraw. That's what my TA does for our lab sessions.
That's amazing.
Yeah. It's impressive at first and then it goes very slowly.
Mhm.
So I'll stick to this. Okay, well, we have these two carboxylic acids and then we heat them and lose water.
Okay, so carboxylic acids and water.
Yes.
Did we learn this reaction?
Maybe not, but you might be able to work it out.
Oh, are you just
Does
gonna
this
get
talk
stuck with a met?
Sorry, what would you say?
I was gonna say you're just gonna get stuck with the carbon after you lose. You're gonna get stuck with a ketone after you lose the alcohol on one of those groups, or on both those groups. Sorry.
So
You're gonna get stuck with the aldehydes.
My money's on it'll be deprotonated carboxylic acids.
something like this.
Yeah, I don't think that's right.
No,
Now that I'm
No.
seeing it,
no, that's weird.
I'm not sure you're getting the hydrogens.
Can I get an oxygen anions on the end of those two carboxylic acids, perhaps?
Okay, but we've lost two hydrogens then, but we're losing H2O.
Yeah.
Total.
Oh, we're losing H2O? Oh, okay.
Yes. Yeah, they tell you that here. That is
then-
useful information.
Then do we have trimethylbenzene then?
So here you would have lost O and then OH. Here you would also have lost an O and an OH. There's nothing you can make with those.
Oh wait, that's O2H. That's not H2O. Okay.
Maybe I'll draw this molecule a little bit more suggestively.
Does
Oh,
it
it's
form a
gonna
ring?
form a ring.
Yes, it does. And what functional group is that ring?
Oh, ester. Epoxide. Whatever. It's the oxygen's going to be jammed in there.
Okay. You mean like this?
Oh, it's a crap phthalimide. However you say that.
Yeah, this is an anhydride.
Anhydride. Okay.
I
Of
think
which
the whole molecule is a phthalide, but
phthalide.
Yeah, this is crazy. There's no way we do this one in class.
yeah, the way I was gonna draw the molecule, by the way, is I don't know, something along these lines, which was
Or maybe
Right.
we did do something.
you have an acid, an alcohol, you heat them together. What are they gonna do, right? So you could, in some sense, you could think about this like a Fischer esterification. In fact, I think the mechanism will be exactly the same.
Makes sense.
Yeah.
I mean, one drawn that way.
Huh?
Yeah, one drawn that way, it makes sense.
Yeah. Yup. Okay. Writing this alcohol, isopropanol now.
Does it make an ester?
Okay. Where?
It would make one off of like the anhydride, like oxygen that's in the chain, wouldn't it? So it'd be like O, and then the isopropyl.
Like that?
Yes.
Paul, you agree?
To be honest, I'm not entirely following this one.
Okay. Okay. Well, then let's draw this one out. Where's this part of the molecule? Okay, there's our anhydride.
I mean, I see the CH2N2 in the next step is going to have us making an ester. So I'm
That's a-
suspect of how we're getting from this molecule that we have proposed to ester.
Okay. So, well, maybe this molecule is wrong then.
I mean, yeah, that's what I'm.
Also possible.
Yes. Okay, so here we have our isopropanol, right? And let's take these electrons and react them, bring up here. Okay. And well, I mean, we've seen these reactions a lot, so we know it's going to kick these electrons up, kick them back down, and then pop off that oxygen. Okay. And so at the end of the day,
Oh, you're going to
what we're
have
left
like
with.
one ester,
Yes, exactly.
and then you're going to get your other one next step.
Yeah. And so this here was just an O minus, which let's just protonate it. Just for good measure.
So let's make that one a methyl ester as well. Or would that be a methyl ester?
Yes, it would.
Yeah.
Okay.
So methyl ester, and there we go. Cool. That is it.
Excellent. All right.
Cool.
And B11, I'm saying we chop the alkene and have two Or, ooh, yeah, doesn't O3?
Yeah, it's ozonolysis, right?
Yeah.
Mhm.
Makes a ketone, makes two ketones.
Yeah, exactly. Right.
Or I
We
guess,
just replace that double bond with 2 oxygens. And that's it. Yep. Yeah, cool.
all right.
That covers B. Let's pick
Wow, so it's A, B,
Problem.
C, and D.
yes. There's
Okay.
C and D.
And okay, so when we have the plus, since toluene,
Oh.
the CH3 group is an activator, so it's a para meta. Yeah, so you would now do a para addition on this one. So it would be the C1 would just be that molecule, but instead of it being para, or instead of it being ortho, it would be para.
Is
So
there
it'd
a different
be-
place we can start? Or okay.
Yeah, there is a different place we can start. Dean, yes, you are right.
Okay.
It is.
Because it's
I
an ortho
don't
para.
even know how you got there, but you are right. It is the same molecule except para. How did you find that out?
Yeah.
Oh,
That was some magic.
isn't CH3 isn't toluene? It's an ortho para director because it's an activator.
Oh, yes, you're
Ah,
right.
from the previous step. Because
Yes.
it's producing two. Okay, I understand. Smart.
Okay, never mind. I also did not remember that.
Doesn't happen often. Every once in a while, I got something.
Yeah, here we go. Ortho and then para.
I always get ortho and meta confused, like just like the naming of them. But
Yeah, I don't know. I don't know if there's any like good mnemonic or anything to remember those.
because I just think of the lines as parallel in para, because like if you
Yeah,
cut through the benzene, it's like parallel. But
that makes more sense.
See, and this is like really stupid, but the way that I remember it is ortho makes me think of orthopedics. And so like when I see the two sort of like next to each other coming off of sort of neighboring carbons, I think of legs like sitting. You know,
that's brilliant. Yeah, that actually really helps. Thank
you're
you.
welcome.
Awesome. That actually okay. I'm gonna actually make a note of that on this thing.
Glad I could help.
There we go.
Orthopedics legs. Awesome.
Yeah.
Amazing.
Nice. Okay, let's say we're going with this para compound here and we put it into acid and ethylene glycol. I don't know if you guys know this compound, but it's
I mean, I know polyethylene. Oh, it's
Oh, we're making a protecting group, aren't we?
you bet. Yeah. Which one?
It's what is it called? It's
acetal.
Yeah. Acetal.
Acetal.
Yes.
I like acetyl better, but I know it's not how you say
Acetyl.
it.
I do too.
You mean like acetyl with a Y?
Like I like the way that sounds better than wait though I hate they're two different things, acetyl and acetal. I don't like that.
Yeah, organic chemists are terrible at naming.
Mhm.
I mean, it doesn't help that this is like, 200 years old of convention. Yeah.
Okay, so NBS, Mg, CO2. Okay, if we learned anything, we know that CO2.
Well, I would start with just the MBS adding to the benzoic position.
That sounds pretty reasonable. And there's only one benzoic position. That's pretty cool, right, guys? Isn't that cool?
That
Very
is so
cool.
cool.
That's right. Yes. There's the bromine, right?
And then we're gonna make a Grignard, and then we can react our Grignard with our CO2, and we're gonna do that kind of ketone sticking on thing,
Yes.
where it's actually gonna be a carboxylic acid.
That's right. And this compound is an absolute unit. Well, all right, maybe. Oh wait, no. Let's write this out. There's too many steps involved, and we're gonna miss something if we don't write out the steps.
Okay, so we're making that terminal bromine a Grignard,
Yes.
or I guess the whole thing a Grignard, but the Mg is cutting into the bromine. And then,
Can't we just replace the bromine with a COOH?
Okay.
oh yeah, it's just gonna make
Catching up
carboxylic
to
acid
you.
with CO2 and H plus. This thing is a complete unit. That's crazy.
Yeah, this thing is big. Okay.
And then
Now
our
we do
H
acid workup.
throws the proton on that carboxyl.
And it reforms a ketone.
There we go. Yeah. Okay.
Okay.
Yes.
Yeah, that's what I would have missed.
Yeah. That's why when I started writing this earlier, and I was like, why don't we actually do out every step? Yes, it was because of that. This is a big compound. Nice.
I still can't get over the CO2, what it does to Grignards is crazy.
It was pretty cool. I like it. I thought it was, I mean, I was salty after my test because I was like, okay, we did not learn this. But when I did learn the reaction, I was like, oh, this is, I can get over the fact that I was, cheated on my exam over,
Quite big of you.
reaction.
Exams
Okay.
would be great if they weren't graded.
Yeah, they would. It would be interesting. It would be cool to learn from them, but nope. Look at this. C4 is done for us. That's cool.
That is nice.
Why don't we just do C5 instead then?
Okay, so SOCl2, we used that earlier.
Yeah,
That
we're gonna make acid chloride.
Yeah.
Acid chloride.
Yeah, both of them, right?
Yeah.
Yep.
So are we just assuming excess?
Yes.
Excellent.
Cool.
I mean, if we weren't assuming excess, it'd be the same molecule either. I mean, it'd be like just a symmetrical molecule, or not symmetrical. It would.
Or like if we only had one equivalent though, wouldn't it like
It
just-
only hit one of the groups, but
Yeah.
like it doesn't matter which group we pick because the molecule that we're
Yeah.
starting with is symmetrical.
True.
Yeah.
True.
In this, also in this follow-up part, there's two equivalents of this reagent.
Okay.
You
So
can guess that. Or that's what leads me to say yes, this is meant to be excess.
Okay, so we did this before. Okay, so we have this. We're going to be making some aldehydes over here.
That's right. Yeah, these are both aldehydes.
I've never drawn compounds this small. It's crazy.
Yeah, I know. Yeah, this is a very large problem. That's why I made this as a giant document.
Mhm.
Okay, cool. And so we went here, we went here. We could just double check that oxidizing these aldehydes will get us back to these alcohols. Yes, correct.
Okay, so
Cool.
carboxylic acids with bases.
Two equivalents of base.
Would that just like make two alcohols on each end? Like would the base attack the carboxylic or the carbonyl carbon, and then it would pop off move the oxygen up, and then base would come in, grab one of the oxygens or something, and then never mind. I don't know what's gonna happen.
Would it be two diols? Oh,
No.
trial.
Don't think about this one too hard.
Would it just be alcohols? It would just be like a two primary alcohols, like one primary alcohol on each side.
Mm-mm.
Two diols.
We're just straight up losing the acid.
Yeah.
Okay,
Wait, what do you mean straight up losing the acid?
it's just coming off the molecule.
No.
Oh wait, can I see the NaOH excess, what it's acting on the bottom? It's adding the amine.
Oh, they're amines in that one though.
Yeah.
Let's see here.
I don't think that one's gonna help.
I don't think we did basic
Oh.
workups with.
Wouldn't it
We're
just
just gonna make the
alcohol?
carboxylate ions,
Yeah.
carboxylate anions.
Yes.
I understand
Yeah.
now what you're saying. Don't think too hard. Okay.
Oh,
Yeah.
what?
It's because I just saw the next step below when we're adding the acid chloride. So that's why we need the carboxylate anions in order to get that crazy thing.
Because NaOH is a stronger base than the carboxylic acid groups. That's
Yeah.
what it was.
I think usually when you're making anhydrides from an acid and an acid chloride, you actually usually don't deprotonate it, I think. I'm pretty sure you normally just add the two together as an acid and as an acid chloride. At
So
least. Yeah.
the anhydride is just an oxygen in between two ketones.
Mhm.
Okay.
Yeah. That's it.
Okay, so where in this insane? Okay, so CA is when the two bromine, the
So yeah,
dibromo.
so here and then here, and now we can go around this way.
Okay.
This is the same reaction as before that we said don't worry about.
Oh yeah. Okay, so this one.
Yeah. So I could just write this one in. It just makes the amines. You don't have to.
So now we're gonna make our diacid, whatever the N2 plus thing.
Yeah.
And then would
And
that go too
then we're gonna
crazy?
use HBF4 to add fluorines.
And wouldn't it just it would just get rid of all the nitrogen and just make it like a difluoro
Yeah.
benzene?
That is all of it. Yes. All right.
Diazonium salts.
We have done C.
I'm not gonna lie, I'm happy D looks small.
I agree with you. Yeah. This one problem is brutal.
So SOCl2, we can make an acid chloride, right? Oh, no, I'm sorry. We're just gonna add the chloride.
Pick a new color. Green. I don't normally use green. Let's see. SOCl2. With an alcohol, what happens? What's it do?
SOCl2. It'll add a chlorine right where the alcohol was.
Yeah,
Yep.
we're
It's
just
just
gonna
substitute.
replace.
Right. Yeah, good catch.
And this one's the Gabriel synthesis, right? So we're making an amine, throwing an amine in there.
Yeah. So we are making an amine instead. Yeah. Nice.
Oh, and then NH2, NH2. We used, that was last week. Why can't I remember what it is? It's
NH2, NH2.
something.
Oh. Wait, so this is using this hydrazine, this NH2, NH2, this is part of the Gabriel synthesis.
Oh, okay.
So here, we're just doing the first step of it.
What is the first step?
Gabriel's.
Oh,
Oh, yeah.
Oh, we're
yeah.
attaching that huge monster.
yes.
Yeah.
Yeah, that is it. So all we are doing here is attaching exactly as you said, this monster.
Okay, so replacing the chlorine with like the nitrogen of the monster.
Yes.
And we have the oxygens coming out, and then that replaces. Then it becomes a primary amine.
Yep.
Yeah, that's it. It's nothing more than that. And then over here, yeah. Okay. Oh, and it also asks for the, well, it tells you what the other thing that comes out is. This is what you get out of the Gabriel synthesis, this other junk.
Mm-hmm.
Yeah. Okay.
Okay, so D3, which is like the bottom left corner of this.
Almost.
Don't we just replace the chlorine with a nitrile?
Agreed. This is just SN2.
Then the lithium aluminum hydride reaction, which we just did a second ago.
Doesn't that turn it to a, like you keep the carbon, turns it into a primary amine?
Yeah, I think it's going to reduce. Yeah, so it's going to add like another carbon to our chain. I think it's a primary amine.
Yes. Right. And as usual, my way of doing this is count. Because I don't know, I'm just not good enough at following to not have to count. Okay.
SOCl2.
We're replacing the amine with chlorine, and then we're gonna. Oh, so shouldn't we just have that same chain with the chlorine at the with an alcohol at the end?
How did you do that?
I just looked at what we did before with the SOCl2.
Okay. That's crazy though. Okay, let's see here.
Because I know we're gonna eventually get like the NaNA3,
Mhm.
the N2 or the
Well-
N3 replacement.
Okay, so the alcohol, then we would get the chlorine, and then the N3 would replace the chlorine, and then H2O and heat would reduce the N3 to an NH2. Or yes. Okay.
So I think this is not it.
Oh,
This is not
that
the
would be
thing.
great.
I think this is another one of those reactions that we haven't talked about. What
I
it
think
instead is the carboxylic acid. Actually, it's not even this one. It's there's an extra carbon here, and then it's a carboxylic acid. So I think, yeah, the way this reaction goes is that you go here. Go to this acid chloride. go here. And then the H3, or the H2O heat, that's the same as the reaction we did over here. Oh, oops, sorry. We had this thing, and so then we heated it, we got this thing, and then we added an alcohol. In our case, we're adding water.
Okay, so that's how
Yeah,
you
make some other stuff. And I guess in the other case, it's just gonna remove this.
And wait, what happens to our acid chloride when we add NaN3?
Aren't we exchanging the chlorine for the N3?
Yeah. Oh, okay,
Yes.
that makes sense. All right.
Yeah. Both of these reactions, this first reaction and the second reaction are things that you should be familiar with. This reaction, you shouldn't worry about. Yeah, I guess don't worry about D5 so much. Yeah, sorry, some of these are unusual for us.
And then D1, is that just carboxylic acids on either side of a benzene ring? Like
I think so.
Like a one, I forget what it's called when you have two carboxylic acids on a benzene.
Yeah, because we're splitting this whole thing
Yeah.
this way to get D1, right? So,
Or since it's H2O workup too.
well, also it wouldn't be carboxylic acids, right? Because we have lithium aluminum hydride.
Yeah. It would be it would be a benzene with two ethanols on it.
Aldehydes?
Let's see.
No.
Where can I
I'm gonna go with methanol. Two methanols.
can I write this out? Here we go. So if we have this thing, and let's say we split it, right? So we split this whole molecule. Plus 2 times, what was it? Phenyl with an acid on it.
Oh, okay.
Okay, so this one goes up to here.
So it's ethanol.
Yeah. Ooh, or is it two?
No, you're right. It's methanol.
Or it's
methanol.
like two. Yeah, methanol is coming off like a carbon, and then
Yes.
that.
Yes, it's that.
Excellent.
And we made it through.
Nice. The timing's pretty good as well.
Yeah, I know. Yeah. Which is unusual. Maybe it's because we started right out and went right into the problems instead of our usual review for way too long and then get through half the problems. Yeah.
I have to say, although I like the reaction maps, I don't know if they're as helpful for me as when we do syntheses, because syntheses, I see all the reactions strung together.
I agree with you. Yeah.
Could we in the future do more like multi-step syntheses? Because those to me are like the hardest to see when you don't. It's not just like one, like what Paul was saying, like when you see multiple things you have to do along the way, because I think those are the hardest ones to conceptualize.
Yeah, I think that's pretty reasonable. Yeah, so I don't make these worksheets. We actually have one person who kind of runs the workshop. I mean, I will tell him to do multi-step syntheses because he normally takes our feedback very well into account. So I will tell him that. So I would expect more multi-step syntheses coming up.
Gotcha.
Cool. All right. Well,
Thanks, Adam.
Yeah, it's
we've
been
done
great.
it.
Thank you.
Thank you so much, Adam.
Awesome. Yeah, I'll see you guys next week then because we managed
See you
to
Sunday.
actually finish. Yeah.